Consider the bases S equal to alpha 1, alpha 2, alpha 3 of R3, the three-dimensional vector space. So alpha 1, alpha 2, alpha 3, these are the bases given to us. We need to express first this vector in terms of these bases. Then secondly, the transformation T is given to us from R3 to R2, defined by T alpha 1, T alpha 2, T alpha 3, and we have to find the value of T for 2 minus 3, 5 vector. So these are the bases given to us, and we need to express this in alpha 1, alpha 2, alpha 3. For that, we can write this 2 minus 3, 5 vector as A alpha 1 plus B alpha 2 plus C alpha 3, where this A, B, C are the scalars we have considered. So writing the value for alpha 1, so this is 1, 1, 1, and then B into 1, 1, 0, and then C into 1, 0, 0. This is your vector. So this further equal to A plus B plus C, and then A plus B, and then A. Let's compare the elements. The first element 2 is equal to A plus B plus C. The second element minus 3 is equal to this second element, that is A plus B, and 5 is equal to A. So we are getting the value of A to be 5. If I put this value in the second equation, we can get the value of B, right? So A is 5 plus B equal to minus 3, and from here we get B to be equal to minus 8. And then from the first equation we have A plus B plus C equal to 2. A is 5, B is minus 8. So we get C to be equal to, 5 minus 8 is minus 3. That becomes 2 plus 3, which is equal to 5. So we get A to be equal to 5, B to be equal to minus 8, C to be equal to 5. That means if I put these values back into this equation, let me mark this as 1, at here, here and here, then this given vector is expressed in terms of alpha 1, alpha 2, alpha 3, right? So from 1, we have 2 minus 3, 5 equals to A is 5, then alpha 1 plus B is minus 8. So this is minus 8 alpha 2 plus C is 5, and this is alpha 3. So this vector is expressed in terms of alpha 1, alpha 2, alpha 3, right? Secondly, we need to find this T of 2 minus 3, 5. We know that this 2 minus 3, 5 is equal to, just now we have found that, this is 5 alpha 1 minus 8 alpha 2 plus 5 alpha 3. So this is T of this vector equals to T of 5 alpha 1 minus 8 alpha 2 plus 5 alpha 3. Because T is a transformation, so we can further write this as 5 into T alpha 1, right? Minus 8 into T alpha 2 plus 5 into T alpha 3. And the values of T alpha 1, T alpha 2, T alpha 3 are given to us. These values are given to us. T alpha 1 is 1, 0. T alpha 2 is 2 minus 1. T alpha 3 is 4, 3. Let's put these values. So this is 5 into, what is T alpha 1? It is 1, 0 minus 8. T alpha 2 is 2 minus 1 plus 5. T alpha 3 is 4, 3. So from here we get 5, 0 minus 16 minus 8 plus 20, 15. Then the first element becomes 5 minus 16 plus 20, and the second element is 0 minus, minus and minus becomes plus. So this is 0 plus 8 plus 15. So 20 minus 16 is 4, and 4 plus 5 is 9, and from here 15 plus 8, that is 23. So the value of t2 minus 3, 5 is 923. This value is in R2, the second dimension, and this is in R3. T is a transformation from R3 to R2. It is given to us. Right? So this is how we do these kinds of example. Next is a beautiful note over here. Let V be a vector space and T is a linear transformation from V into V. Then which of the statements are equivalent? Then the intersection of range of T, this is equal to the 0 subspace of V. It is the 0 subspace of V, right? Then second, T of T alpha 1. If this is equal to 0, then this implies this T alpha 1 is 0. Please remember, this is your 0 vector in V. Right? Okay. Next is linear transformations as vectors. Let LUV or homomorphism from U to V be the set of all linear transformations from the vector space UF into VF. So if we are having the set of all linear transformations and if we need to impose a vector space structure, if we impose a vector space structure on this, on all these set of linear transformations over the field F, then for this purpose we define the scalar multiplication and addition in set of these linear transformations. So for the scalar multiplication and addition in set of these linear transformations, we impose a vector space structure on this. Okay, what is the scalar multiplication and addition in LUV? Suppose U and V be the two vector spaces and T is a linear transformation from U into V over the field F. If I take any element from this field F, let's say C, then this C multiplied with T of alpha is equal to C multiplied with T alpha. Here C and T are multiplied together and in the result we have C multiplied with this T alpha. Please remember this. For all alpha belonging to U. So this is a linear transformation from U into V. If I take T1 and T2, two transformations, the linear transformations from U into V, then the function T1 plus T2 of alpha is defined to be equal to T1 alpha plus T2 alpha for all alpha belonging to U. The scalar multiplication and addition, right? So this is a linear transformation from U into V. So the set of all linear transformation from U into V together with the addition and scalar multiplication. So this complete is a vector space over field F. Next is the dimension of LUV. If UF and VF are the finite dimensional, then the vector space of linear transformation from U into V, the vector space of linear transformation is also finite dimensional. So when we talk about the vector space of LT, that means the scalar and addition multiplications are already included. So here ends up the lesson 3. Okay, thank you.